might be the last time we ever have a 10-minute break. People who have taken my class know that I don't like to have 10 minutes break. What I like to do is I like to just do the course from beginning to the end, and then we finish 10 minutes early. Okay, so if everybody's good with the deal, we are going to just have continuous class from now on. And you can, if you never need to go to the restroom or whatever, I want to take a break, you can just leave the room anytime. You don't need to. You don't need to raise your hand and say, hey, I want to go out. No. You can just go out anytime. I'm also not a fan of doing attendance check. So if you don't want to come to class today, it's totally fine. Nobody will bother you, okay? So no attendance check, no 10 minutes break. In the future, we're going to finish 10 minutes early. That's the plan. Okay. All right. Okay, so if everybody's okay, we're going to start our first lecture. Right? Now, the first lecture is an introduction. I'm going to walk you through the major themes in this course. It's going to broad overview of the key topics we're going to talk about, as well as giving you a sort of like a preliminary preparation for what we're going to do in the future. Right? If you go to the website, okay. So we're doing introduction today, and maybe next class, right? We're going to do introduction this week. And this is really the first formal lecture. Okay, so this is not. So what we're doing today is really a preview or overview of what we're going to do throughout this course. Okay. All right. Now, data. As we know, we live in an age of so-called big data age. So data is really everywhere in our world. And data is really today. Data consists of many different formats. We can analyze many different types of data. Sometimes we call it heterogeneous data. Okay. So this is one type of data. It's a purchase history by a consumer on Amazon, which, buy some cheese today, buy some. So this data is really nice, sort of organized, right? So this is what the person purchased. This is the price at which the person purchased. This is one kind of data. We also have ratings data, right? So the first one is, this one is purchase data. This one is rating data. You can see on Netflix or some our local movie rating, like Douban, right? You can see that people rating the movies. That's also something that reflects consumer preference. Okay. And there's also document collections. We have huge amount of collections of documents and texts, and how to analyze textual data. That's also another important topic today. Financial markets, right? We're all familiar with that. Right? So all these things are different and this is social networks. Okay, social networks are tweets by Donald Trump and organized by time, right? From 3 a.m. to 9 p.m. These are the positive. So if we analyze Donald Trump tweets, we can separate them into positive tweets, negative tweets. Like Kim Jong-un is short and fat and stuff like that. So we can analyze social network data. That's also another type of data that's going to be very useful today. So all these things are essentially heterogeneous data, like very different kinds of vast amount of data we can analyze today. But how to analyze them? That's really the topic of data science. Right? Now, in data science, we have what I call, data science is something that without a clear definition. Right? Nobody really defines what data science comprises of. But we hear some typical traditional disciplines. One is machine learning, statistics, and of course including econometrics. Right? So all these things can be sort of grouped under the umbrella of so-called data science. Right? Now, all these things are different. Okay, these disciplines are all different, but they also share a lot of commonality. There's a lot of common theme to all these different disciplines. They're developed by different fields. Right? So machine learning comes from CS, computer science, statistics, econometrics by the economics field. So they have different language and they have different tradition of doing stuff. But in our lecture, in our course, I hope to show you that they share a lot of commonalities, and it's actually possible to put them in a unified framework for you to understand what everybody's doing. Generally speaking, in a very generalized way, the difference between them today is that as we move from here to here, right, as we move from machine learning to econometrics, the focus moves from prediction and a pattern discovery, okay? Discover the patterns in the data, and then making very nice, accurate predictions. We move from there to inference about causality and the underlying mechanisms. So traditional machine learning is concerned primarily with how do we make really, really accurate predictions given our data. How do we find out the patterns within the data? Right? But traditional econometrics is about discovering, estimating economic models and discovering the underlying causal relation between variables. Okay, so this is really the traditional difference in their focus. But of course, everything is fluid. Okay, everything is fluid, and today these disciplines borrow from each other in everything that they do. Okay, so this course aims to give you a unified view about all this different stuff. Okay, all right. Now, this example to show you why these disciplines share a lot of commonalities in what they do in terms of the underlying technique and spirit. Let's first look at example that's completely irrelevant to economics, right? So this is a classic example in what computer science does, which is how do we discover which one is a chair? Okay. So suppose my question here is I give you all these images, and I want to recognize which one is a chair. Right? I can see, is this a chair? Yes, this is a chair. Is this chair? Probably not. This is certainly not a chair, right? Well, this one chair. Okay? So I give you every image. I show the image like a monkey and ask you whether it's a chair. If you answer yes, that's a 1. If you answer no, that's a 0. That's called classification. Right? It's very simple. Classification. That's called classification in computer science. Now, do we do classification in economics or business? Right? Do we do classification? Yes, of course. Okay. We do plenty of classification. Now, for example, if you work for in business, if you work for the bank, credit card department, and suppose you work over risk control, risk management for the credit card department of a bank, then what you do is you want to analyze the risk of a consumer who has your credit card, whether he will default or not, right? Whether the consumer will default or not. So you have some data. You have data on a person's income. You have data on how much money he has already borrowed so far, right, from other banks, the balance, right? And you want to tell. And you know that historically, these are data. Okay, so I have some data on other consumers whose income is this and whose balance is this, whether they default or not. So the red dot is first people who have defaulted. The blue dots are people who have not defaulted. Right. So you want to discover their relationship, but that's also classification, because what we're doing here is we're also answering this 0-1 question. Give you any consumer. Give me any consumer whose income is here. Whose balance is here. The question is, will he default or not? If he's going to default, that's a 1. If he's going to not default, that's a 0. You're making prediction, right? So this kind of prediction is also classification. And then exactly in the same spirit as what we're doing, whether it's a chair or not, okay? Whether it's a chair or not chair, whether this person will default or not default, that's the same, underlying these two seemingly very different questions are the same underlying spirit and technique in data science. Right? So that's what the commonality is. Now, we are familiar with regression, right? So this is a regression that's mostly done in agricultural science, where people want to know the difference between temperature and the crop yield, right? So when the temperature is high, the crop yield may decrease. That's one of the examples I picked from a paper which predicts the impact of global warming on crop yield, right? So we have this relationship between them, and we can do a regression. So this is in agriculture. Do economics do regression? Of course, right? We do plenty of regression in economics. The relationship between government debt and GDP growth of a country is data like this, and we can draw the line, and that predicts the regression relationship. So whether classification or regression, these are the things that we do in computer science, we do in agriculture, we do in economics, we do in every applied data analysis programs, data analysis disciplines. And they all share the underlying same principles of data science. Okay, and by the way, what is regression actually? Right? Many people who are trained in econometrics have a different definition of regression, maybe understanding than the CS people or stat people. Regression and a classification, the difference between them, as defined in machine learning today, is actually very simple. If the y variable, right, so here we are trying to predict whether this person will default or not. So this y variable is default or not default. So it's a 0, 1. Okay? So if your variable is discrete, if it's a 0, 1, that's a classification problem. If your y variable is continuous, like here, the yield, right? Yield is a continuous variable. So if your y variable is continuous, we call it regression. Okay? So it's really, it's a very broad definition of what regression and classification is. And in this course, we're going to cover them. Now, another kind of different task that we do in all these disciplines is called supervised versus unsupervised learning. So what are supervised, what are unsupervised? Well, let's again take a look at the computer science problem, not economics, right? So in computer science problem, we have a vending machine. The vending machine, every time you put some coins. Now today nobody does coin, right? We do Alipay, we do all this. But imagine a prehistoric vending machine, right? So in that vending machine, we still put in coins. Now there are different kind of coins. There's $1, there's a 10 cents, 5 cents, 25 quarter. Right? Now we want to write a program, computer program, to tell the vending machine to automatically recognize whether the coin people put into it is a 10 cents or 25 cents or which type of coin it is. So the way it does is that it measures, the vending machine measures the mass and the size of the coin, because the coin are not that precise. So they actually overlap. So it measures the mass and measure the size of the coin, and then try to see whether it's which type of coin it is. Now, what is supervised learning? Supervised learning is we have some data. Okay? The data is the mass and the size of different types of coin. So I know what they are. I know these are 25 cents. I know these are 5 cents. And I just want to write a program so that when I'm given an unknown coin, I can accurately predict whether the coin is 25 or 5. Okay? So that's supervised. Supervised meaning I already know. So in my data, at least, right? In the data I used to sort of estimate my program, I already know what the y value is. So what I want to predict. I know these are 1. I know these are 5. Okay. So now based on this data, what I can do is I can say, okay, I can draw a line here. I can draw a line here. I can draw a line here. And I can say, okay, anytime I receive a new coin whose mass is here and the size is here, for example, then I will predict that this coin is a 25. It's very simple. Right? It's called supervised learning. Now, unsupervised learning is harder. Right? Unsupervised learning is harder. Unsupervised learning is I do not know what these coins are in my data. In my data, I do not know what these coins are. I have no idea. I just see these coins. Right? There's a mass, there's a size, but I don't know whether this. I have no idea. No, this is 25. This is 5. This is 1. But I want to write a program to automatically recognize that these are different kind of coins. We will never know which one is 25, which is 1, but at least I want to discover some pattern in the data. Okay? So looks like, for example, let's look at this, right? Let's look at this graph. So based on this graph, it looks like this coin, this type, these points belong to the same coin. Okay? So it looks like this is one type of coin. It looks like this is one type of coin. And then I'm not so sure about here. So maybe these are a different types. Maybe these two together is a different type of coin. So based on this data set, if I want to discover the patterns in them, I can say it looks to me that there are 3 different types of coins. Or maybe 4, right? Or maybe 4, I don't know, okay? So this is called pattern discovery or unsupervised learning. So unsupervised learning is now knowing the value of the y variable, and we just give me a bunch of x, and I want to discover the pattern in it. That's called unsupervised learning. Right? Now this is done a lot in computer science, but do we do it in economics? Of course, right? We do it in economics all the time as well. Basically, whenever we have, for example, latent, in economics what we talk about is latent type of people or of individuals, right? So for example, suppose we have a bunch of consumer purchasing data. So this is the price of a good. This is how much people purchase as a result of the price. Now, here we have here I have a red and a green. Right? So I tell you that there are actually 2 kinds of people. So these people, red people, are the people with higher income. So they have lower elasticity. So when you increase the price, they do not decrease their purchase a lot. But these people this green type of people they have lower income. Okay, they have lower income. That's what I know. And if you see, it's very obvious. If you increase the price, these people decrease their purchase a lot, right? The demand decrease a lot. So they have a higher price elasticity of demand, right? Now, if I tell you that these are 2 different people, and then I want you to model that, right? Write a statistical model to describe these two, the elasticity of these 2 people, that's called supervised learning. If I do not tell you, okay, so suppose, I don't have it, right? Just imagine, okay, imagine there are no colors. Imagine we just have all these data points without colors. And I want you to tell me, okay, the elasticity of these people, and I want you to discover by yourself that there are actually 2 different types of people here, and they have different elasticities. That's called unsupervised learning. As you can see, the unsupervised learning is a little bit harder, right, than supervised learning. It involves a lot of guesswork. and it may not be as well as precise as supervised learning. Right? But these are the tasks that we do in economics. These are the types. These are the type of tasks we do in computer science. These are the type of tasks we do in every kind of disciplines today. Right? So they share a lot of commonalities, and they all have the same underlying technique. So that's what I'm going to teach you in this course. Okay, we're going to do. All right. Just show you some applications for the econ people, right? All of you are econ people. You may know this paper already, right, by Bahari in the 2015 AER. That's one of the first papers published in top journals in economics that introduced machine learning methods into economics. As you can see, this is very recent, right? 2015. It's a very recent paper, and what they did is very extremely simple. What they did is they do essentially a simple demand estimation, but they try it. So traditionally in economics, how do people estimate demand? People use logistic models. People use panel data models, right? And what they do is they say, okay, let's try some machine learning models, and let's compare the machine learning results with traditional econometric models, and let's see how well they perform. And here is, right, so if you have time, you can look at, we'll see this later, but here's the main conclusion. In our results, we find that the 6 models we use from statistics and computer science predict demand out of sample in standard metrics much more accurately than a panel data or larger model. Okay, so that's a logistical model. That's what they say. Okay, all right. So this is really one of the first papers that try to sell the virtues of using better models, statistical models, for estimating demand than traditional econometric models. If you look at this table, then the out-of-sample error that they talk about is essentially these numbers. So the best performing model here is random forest. So random forest is the model they give you, at least for their task, for their project. The random forest give them the best predicting power than any other models they have tried, including panel data, fixed effect models, and logistic models. Now, if you don't understand what random forest is or what all these models mean, you will by the end of the class. In fact, by the end of this course, actually by the middle of this course, you can do this paper by yourself as a student, as like a 1-week project. It's really a simple one. Okay. All right. So that's the goal. Now, but this is only the first part of this course, where we are only concerned with statistical models and how to find the best statistical models, including machine learning models and econometric models, etc., for some task at hand, how to model the data. The second part, we're going to advance to causal inference. And by advance, it's because it's harder. Okay, so the causal inference is harder than simply doing statistical prediction. Right? Causal inference is about understanding not only how to use X to predict Y, but whether X and Y has any causal relationships, and how much is that causal effect, if there exists any. Right? But so if you read so what I'm saying here is learning patterns is not enough. Right? The key idea is learning patterns in the data is not enough. Machine learning is all about learning patterns in the data, but that's not enough for us because we are social science. Economics is a science, and what we're trying to do is not only discovering patterns, but understanding where those patterns come from. What are the mechanisms, right? The causal mechanism that generate those patterns. So we want understanding, and any discipline that wants understanding, essentially you can say they're a science, right? Of course, if you use scientific methodology. So here's an interesting little story by Bertrand Russell. The Bertrand Russell talks about a chicken, right? Supposedly smart chicken. So this chicken discovers a pattern, which is every morning at 8 o'clock, somebody will come and feed him. Okay, so that's a pattern. Right? Day after day, when the sun rises, somebody comes and feed the chicken. So that's a nice pattern that he has discovered. 8 o'clock. So based on this pattern, the chicken predicts that tomorrow I will wait until 8 p.m. Right? So the chicken rises early. Chicken rises like sunrise, like 5:30 or something. And then I'll wait until 8 a.m. and this guy will come and feed me. Right? So that's the pattern he discovered. Until this prediction fails. Why? Because on Christmas Day, somebody comes and instead of giving him food, that person kills him. Right? Kills the chicken and feeds to people. Now the reason why this prediction fails is not because the pattern that the chicken discovers earlier was wrong, right? That's a pattern. Every day, feed him. The reason why the prediction fails is because the chicken doesn't understand the underlying reason why people are feeding him, right? It's not because they want to feed him just for feeding him, but because they want to eat him in the end, right? So without understanding the causal reason, right? Without understanding why, the prediction always fails in the end. Right? So if you only base your prediction on some pattern, then every pattern will ultimately change because every pattern is generated by some underlying mechanism. So if you don't understand the underlying mechanism, your prediction will only hold within a very small range. If you want your prediction to hold well for a long period of time or for the wide range of data, then what you need to do is really understand the underlying causal mechanism. So that's why we want to do causal inference. Right? So not only help us understand as a science, but also help us to make actually better predictions that holds for a long, long time. And when environment changes, when the underlying mechanism changes, our prediction can still hold true. Right? So that's really the benefit of doing causal inference, and it's very, very important. Okay. Right. Okay. So causal inference is really a field that's not only useful for science because we understand it, but also useful for industry when they really want their prediction to be robust to changing environment. Right. So that's why, for example, Microsoft today has started a causal inference lab, especially devoted to this kind of effort. Now, broadly speaking, I like to define causal inference in two kind of different tasks. The first kind of task is called causal effect learning. Right? Suppose I give you x and y, right? So if I ask you, does x have any causal effect on y? And if yes, how large is the causal effect? That's called causal effect learning. Okay? That's called causal effect learning. Now, causal mechanism learning is it's much harder. Causal mechanism learning is not only am I interested in the causal effect, I'm also interested in the mechanism. Like, why does X have a causal effect on Y? What is the channel? So this is a much harder question to ask. To give you an example in economics, right, many Chinese economists have done research on, for example, whether building a highway or building a high-speed rail increase economic growth, right? So you can have a bunch of data, where the data is high-speed rail connections in China between all these different cities, and you have the local GDP of different, economic output of different cities, and you want to see whether building a high-speed rail has a causal effect on GDP growth. That's called causal effect learning, right? So you can say, okay, suppose building a high-speed rail increase GDP by 1%. Suppose, okay, just give me an example. That's called causal effect learning, because all we have learned so far is an effect. This effect is 1%, 2%. Right? A much harder question is why. Suppose you have established in causal effect learning that building a high-speed rail increase economic growth by 1%. Suppose. Then the question is why? Because there are many, many reasons why this can happen, right? So for example, maybe it's because of local labor market integration. The labor market is more integrated, or maybe because it enables people to travel faster. That's a sort of like efficiency argument. Or maybe because it allows people to invest in less developed areas that previously was not reachable by slower modal communication. So that's a sort of capital movement or investment story, right? So we have different kind of stories that we can tell that explains this 1% increase. That's called learning the causal mechanism. And that's a much harder task than learning a simple causal effect, right? So, by the way, so for all of you who have already studied some basic econometrics and statistics, you all know this very simple point, which is correlation is not causation. Right? So we can have a lot of correlation between two variables. So this is gold price, and this is crude oil price. So oil price and gold price over a long time period horizon has a very high correlation with each other. Right? So you can use. So if your goal is only predicting, so if your goal is predicting gold price, then oil price is something that may be helpful to you. Okay? You can use oil price to predict gold price, and that's it. If your goal is prediction, that's what you do. But if you're an economist or financial economist, you want to understand why. Okay? What is the mechanism that really links these two time series together? And that's much harder to answer the question. Right? So that's causal mechanism that we understand. Okay? This is a classic example in microeconometrics. Right? So all of you who've taken any course is probably fed up with this example because it's just too much, right? Every book starts with the example, education and learning, right? And the reason why partly is because textbook writers lack of imagination, but another reason is simply this is a great example, right? So we see this strong correlation between the years of education and people's income. The question is really how much is the causal effect, and then what is the mechanism? How much is the causal effect means look, how much of this increased income is really created by education? So that's a causal effect. The mechanism is how does higher education, how does more education actually increase your income? Like what is the channel, right? So we have, for example, you all know that people have different ability. So high ability people acquire more education, so that's like a sorting or self-selection effect. Or education may itself increase your ability. Or maybe we have sort of like an incomplete information story where it's the sheepskin effect, right? Because the employer doesn't see your ability, you need to signal your ability by acquiring higher education. So so education essentially takes on a signaling effect, and that's an incomplete information, labor market information story. So we have all different mechanisms that can create this positive correlation. How do we find out which one is the correct one, or how much they contribute to our final conclusion is essentially the causal inference thing that we really care about, right? So that's the difference between the first and second. So as you can see, causal inference is harder to do than simply discovering patterns and making predictions. So that's why our course is scheduled in two parts. First part, we talk about prediction, machine learning stuff, and the second part, we'll use whatever we learned from the first part to advance to this more harder and deeper question about causal inference. In economics, in microeconomics, causal inference also there's a name for the entire field called programming evaluation, which is concerned with evaluating and predicting the effects of government policy. So this is the type of research, causal inference research, that we do a lot in microeconometrics, right? So for example, the effect of worker training program on employment, the effect of early childhood intervention on adult outcomes, the effect of negative income tax on labor supply, the effect of environmental regulation on firm pollution, right? All these questions essentially are causal inference questions. We want to know the effect of something like a government policy or program on some outcome we're interested in, right? So that's the major concern of microeconometrics. Okay. Now, finally, let's talk about where the future may go from here, right? So this is purely conjecture. This is not real. This is not agreed upon. This is pure conjecture. And lots of it is my own conjecture, right? Let me just say that. So far, the way that we do causal inference in economics, or also in physics and chemistry, in natural science, the way that we do causal inference is consisting of really two groups of people. They work together toward a causal inference. The first group of people are called theorists. Right? So economics, we have economic theorists, microeconomic theorists. In physics, we have theorists who develop theories like quantum mechanics, right? Like in economics, we develop theories, supply, demand, all these are theories. So the theorists develop theories about how things work, and then there are the applied people who work in labs or who take observe the data, and they try to verify or estimate whether a certain model works or not. Okay, so these are two groups of people working together. Theorists propose models, applied people or experimentalists verify the model or do things that explore the patterns in our in our world. Okay, is there any way to essentially combine them into one? Okay? Is there any way to allow? Suppose you can write a super computer program. Is there a way to write a single program that can both propose models on how the underlying mechanism is, and then automatically test it using observed data, or do some kind of experimentation, and find out what the best model is? In other words, is there any way to automatically do everything that we're already doing using two groups of people? Right? Now, if we can do that, then what? Then we essentially arrive. Then that's essentially the ultimate goal of AI in the future. Right? So if you ask me what is the goal of artificial intelligence into the future? Well, the true signal of intelligence. What is the true signal of a computer having intelligence? Well, it's not today. Okay, today if people talking about artificial intelligence, you see people say, okay, this computer is really intelligent. It can self-drive. Okay, so we can design a car that can self-drive. There's not so much intelligence there, because why? Because that's still pattern discovery. We're still discovering the patterns in the image. Okay, in the image, and we know, okay, given the image, I can tell this is a tree, this is a person. Right? That's all image recognition is self-driving car technology is based on. So this is essentially still pattern recognition, which is the first part of our course, right? like I said, the difficult thing is not pattern recognition. The difficult thing is causal inference, essentially understanding the underlying causal mechanism. So the true test of intelligence is if we can develop a program that can automatically do causal inference. So if we can have algorithm that can do causal inference by itself and discover the not only causal effect but also causal mechanism learning, then we have truly arrived at the true artificial intelligence age, in which case the computer can do causal inference, so that there's no need for scientists anymore, right? There's no need for theorists to propose models. There's no need for applied people to do to verify those models. The computer program will automatically propose models and verify them using up data. And this is not some future fantasy, right? Because people have already done work in this field. So far, it's called causal search, right? For example, there's this field called causal search. And this causal search the goal is, how do we automatically search for mechanisms, for models that explain the observed data, okay? And people have already done some work, but it's still in an infant age. We're far from reaching there, right? But it's a field that's ongoing. And to me, this will probably be the future, right? We have a unified sort of artificial intelligence or data science field where we can do not only pattern recognition and discovery, but also do causal inference, okay, in the future. All right, but that's not going to be what I'm going to talk about in this course, right? Because they're still far away in the future. All right, so like I said, we have essentially two parts to this course. We have statistical learning, and we have causal inference. I'm going to divide it into two parts, right? Okay, I'm going to jump over them. We have how much? I think we have about 9 minutes, 10 minutes. So let me go on to give you an introduction of statistical learning. Right? So what is the first part about? The first part is about statistical learning. Now, statistical learning is, in a nutshell, is a very simple task. Suppose I give you variables x and y. How do we predict y based on x? Well, that's the question, right? So now, first of all, the first question is, if I give you a variable x and y, how do you characterize the relationship between these two variables? Well, the relation between these two variables is completely captured if you have the joint distribution. Right? You have two statistical variables, and I want you to give me a description of the statistical relationship, then that's completely captured by the joint distribution. But of course, in most cases, we're not interested in knowing the entire joint distribution. Especially if you have many variables, the joint distribution is gigantic, and it's very hard to estimate. So in many cases, what we're interested in is in prediction, which means if I give you x, tell me what is the best value for y. Give me a prediction of y. Now, if I want to do that, then what I can do is this. There we go. Okay, I'm going to write on this board. Right. So suppose our task is very simple, right? I give you a y, I give you an x, right? So we have a bunch of data. It's not a bunch of data. Now, the goal is to give you x, and you tell me what y is. Right? Now, to this end, I can write y equal to fx plus e. Okay, I can write that. Okay. So the first question is, suppose I observe all the data in the world. So these are all the data in the world, okay? And I want you to give me an f. I want you to give me an f, the best f that helps me predict. So I want you to know what this f is. What is this f? What is the best f that can help me predict y? Okay? So that I would say y hat. Y hat means my predicted y, okay? So my prediction y will just be my f, right? Will just be fx, okay? Because the e is just things that I cannot explain based on x. Okay? So what is the best f? I can try. Remember, f is a function, right? So for each x value, I can only have one value, one prediction. So if it's a function, then essentially it's something like a line, right? Okay. So it's so this is one type of f, right? This is one function. So if I have this function, then based on this x, my prediction of y is here. But these are my data points, right? Now, this is another kind of f. Well, I can draw many. Right? I can draw numerous f. The question is which f is the best? that helps me to most accurately predict y. Do people know which f is best? What f is the best? How do we answer this question? How do we know which f is the best f for predicting y? Suppose you observe all the data in the world, right? So this is the entire universe. What is the best f? Is the best f a linear regression model? Probably not, right? Probably not. Now, it turns out the answer to this question, there's no correct answer. Why? Because the answer to this question depends on what do you mean by best. That's the key, okay? So when I say which f best predicts y, I have to first define what I mean by best. Okay, what I mean, because there are different definitions of the so-called best. So, so let me just ask you. Suppose I give you just a random f, right? Just a random f like this. Now, in order to say this f is better than this f, I have to say something about why this is better. I have to define what is best or what is better. I'm going to define it by saying that this f makes less error than this f, right? That's what people typically do. So we'll define what we mean by best is the f is the function that makes the smallest amount of error, okay? Right? Meaning that it's most accurate. But what do we mean by smallest amount of error? Right? Okay. What do we mean by that? So I give you, so again, we can write this. We can always write y equal to fx plus e. If I have any f, then the error. So this is my prediction, right? This is my prediction. Now, the error I make essentially is this e, right? So I want to minimize this e. But of course, at every point, there's a different e, right? So if this is my x, then the amount of e, so this is my e. And here, in this point, I make another different e, right? So every point is a different e. So I have a lots of data set, right? Now I goes from 1 to n, I have n data. So my total e, the total amount of error I make, is y minus fx. This is y. This is my prediction, and yi xi. Okay, yi xi. And then I can what? I can add them together, right? Okay. But do I just add them together like this? Should I define this as what I mean by the total error that my model makes? No. So what is the error that how should I define error in this case? What is the error that you define in linear regression? Very good. Okay. Define it square. Now remember, this is only what? This is only one definition of what we mean by best. It's not a universal definition. This is just one definition. So in linear regression, what you do is you say, okay, I want to minimize this, right? I want to minimize this. So you're saying that I want this error to be as small as possible. That's your definition of what is best. Your definition of best is how to minimize this. But this is only one kind of definition for error. And this is called L2. We'll call this L2 error. Or a term that you may be more familiar with, this is called MSE, right? Mean squared error. Okay? You're familiar with. But that's not the only definition we have. Let me give you another definition, which is the summation of I, okay? Taken the absolute value of yi minus f. Let me just ei, right? Let me just write ei. Okay? So this is what? This is, I can write this as ei squared, right? Ei squared. And I can write this as ei absolute value. Can I use this one as a definition of error? Can I minimize this one? I can do that too, right? That's another definition of what we mean by best, right? So if I minimize this one, that's also, another definition of best. So which one is better? There's no answer. There's no answer which one's better. Lots of applications you want to use this one. In lots of other applications you want to use this one. Okay? They give you different f. Now the key point is, depending on what you define, depending on your error definition, depending on what you think is the best, they will produce different f for you, okay, as a different result. Okay? Now this is called L1 error because it's absolute value. This is called L2 error because it's a square. Now the L2 error give you, suppose we want to minimize the L2. We want to minimize this error. That's our definition of best. What kind of f? What kind of f minimize the L2? What kind is best? Well, it turns out very easy. Fx is simply equal to expectation of y given x. That's it. So if we minimize the L2 error, the MSE, okay, the squared error, then we get expectation y given x. Now, what if we minimize this one? If we minimize the absolute value of error, the L1 error, what we get is, anybody knows? No? We get is median, okay? Median y given x. We have different function as a best, depending on what your definition of best is, okay? Depending on what you want to minimize. Right. So as you can see this course, we'll stress this point again and again. Every time you want to find a solution, what is the best statistical model, what is the best way to describe the data, the first thing we need to do is to clarify what you mean by best. And in data science terms, that means the first thing you need to do is to define your loss function. Okay, so this is called a loss function or error measure. Okay, so we'll talk about it in our next lecture in depth, but this is always the first thing you do, defining what is the best. Now, let's do another example, right? So that example may be simpler. Suppose like me, so we don't have x and y. We just have x. Okay, we just have x. No x and y. Now, let's say we just have y. Okay, we just have y. So what is this y? This y is the income distribution. So this is the income distribution of China. Okay, the income distribution of China. Probably looks like this, where a lot of people are here, and there are some extremely rich people, right? Okay, so that's sort of like an income distribution of China. Now let me give you several different numbers. Suppose, okay. So this is the highest point of distribution, and let's say this is I don't know 10K, okay, 10K per month, or maybe that's maybe let's say that's 5K. What is the let me say this one is this one. All right, I have 3. Okay, all right, great. This one is 10K, and let me just say this one is 15K. All right, okay. So I have 3 numbers here. This is called what? This is called a mode. This is called a mode. The mode of a distribution means it's the point where the distribution is the most likely. So it's the most likely. The probability is highest. So this mode is the point where the probability is the highest. Okay, this is the largest. Now these two, one is median, and the other is mean expectation. Which one is median? Which one is mean? Okay, very great. All right, so this should be the median. Okay, so this should be the median, and this should be the mean. Okay, this should be the mean. Right? Everybody agrees? Okay, because it's skewed, right? It's a skewed distribution. The mean should be higher than median. In this case. Okay, so now here's the question. Suppose you know this distribution, and this is the distribution of China, right? And my question is, suppose I give you a random person from China. I just, there's a computer program that just tells you, look, this is a random person. You don't know anything about that person. You don't know he's male, female, whatever. You don't know any information. I want you to give me a guess of how much that person makes. What is that person's income? What is the best guess you can give? Should you guess that person is 5K, or 10K, or 15K, or any other number? Which one should you guess? What is the best guess we can have? Any volunteers? You don't have to raise your hand. You can just, if you want to answer, you can just answer. All right, I'm going to do a polling. How many people think 5K is the best guess you can get? Okay, how many people think median? median is very, very unpopular. Okay, what about mean? Nobody. Okay. All right. So it looks like mode is most people suppose mode, right? The answer is I think probably the most people who have not raised their hand gets the correct answer. The correct answer is everybody is correct. Okay, you can guess 5K, you can guess 10K, you can guess 15K. There's no correct answer. Why? Because we have not defined what do we mean by the best guess. Okay, so in order to answer this question, you have to first define what do we mean by the most accurate guess. So for example, suppose I give you a random person, right? Let's just say a random person. Now this random person's the true income is Y. Your guess, okay, is Y hat. This is your guess, right? And then, what do you want to minimize? Do you want to minimize Y minus Y hat square? Do you want to minimize this, right? Expectation. Do you want to minimize this? Or do you want to minimize absolute value of Y minus Y hat? Or do you want to minimize something else? Okay, let's first talk about these two, okay? So if you want to minimize Y minus Y hat square, which one should you guess? You should guess the mean. Great, okay? Because the mean minimize the squared loss. It's called a squared loss. If you want to minimize the absolute value of Y minus Y hat, what do? You should do the median, right? Because the median minimizes this. Now, before talking about the mode, in 1 second, right? Let's talk about in what case do you want this? In what case do you want this? Now, if you only want your error, right? So this is the error, right? So if you only want your error in your guess to be, you're not concerned. So what is the sort of advantage of this versus this, right? If you do squared error, then it means that you're really concerned about very large mistakes, right? Because the squared error penalizes large error more. So suppose the true value is 100 and your guess is 10, right? That's a big mistake. But the big mistake here is only 90. The big mistake here is what? 81,000, right? That's a huge number. So if you use this error measure, if you use this loss function, then you really don't want you really want your guess to be higher than 10. If you use this one, maybe you don't care that much, right? So the squared error really guards against really large, really bad guesses, essentially. Okay? So the squared error guards against extremely bad guesses. If you make a large mistake, it really penalizes that. That's sort of like one key difference between the two. Now, computationally, there's a lot of difference between the two, right? So this one is easier to optimize. We'll see that later, but not today's topic. Okay, not today's topic. What gives you the mode? What kind of error you minimize will give you the mode? Well, if you want to minimize this, okay? So the loss function that will minimize the mode is I Y minus Y hat. Okay? Now, do people know what this I typically means? Indicator function, right? Which means that this is equal to 1. Okay, this is equal to 1 if Y is not equal to Y hat. It's equal to 0 if they are equal, right? Now, this is a loss function. This is the error measure, meaning that we want to minimize this. What do we mean by want to minimize this? We really want it to be 0, right? So we really want if this is our loss function, then what I'm doing is I really want my Y to be equal to my Y hat. And if I make a mistake, if my guess is not the actual value, what do I get? I just get 1, right? I don't care how much mistake, I don't care how much mistake I make. As long as I make a mistake, as long as I have any error, that's the same to me. I just want to make my guess exactly equal to the true value. How do I maximize this? Okay, how do I maximize the probability that my guess will be 100% accurate? How do I maximize the probability? Well, I pick the point where it has the highest probability. Okay? If I pick the point that has highest probability, then I have the highest probability of guessing exactly right. That's why if I minimize this loss function, I will get the mode. Okay? I will get the mode. So in summary, right? What kind of prediction you want to do? what kind of function you want to use to model the relationship. First depends on what do you mean by best. Okay, you first have to define a loss function or error measure that that have similar terms. You first want to define what do you mean is the best, and then we pick our best way to do that, and then we give our best prediction based on that. All right. Now today I think we're running out of time already, so I'll stop here today, and we'll continue next time. I'll try to finish the introduction in next lecture. Okay. All right. So let's finish today, and if you have any questions, you can ask Muqing or me about this course.